We'll have the next session 2 of day 3. I welcome Mr. P.Rajendra, Application Engineer, Entuple Technologies, Bangalore, who is going to deliver the lecture in AI-driven EDA tools. On behalf of R.M.D. Engineering College, the management principal, and my own behalf, I'll welcome Mr. P. Rajendran. I invite Srinidhi to introduce the uh, guest. Over to Srinidhi.
Good evening, everyone. It's my pleasure to introduce our guest speaker of today's session, Mr. P. Rajendra, who is currently working as a field application engineer at Entuple Technologies Private Limited, Bengaluru. Mr. Rajendra completed his BTech in Electronics and Communication Engineering from Narasaropeta Engineering College, Andhra Pradesh, in the year 2020. Soon after completing his studies, he began his professional journey
Ma'am,
in the VLSI industry industry as a field application engineer, marking the start of an exciting and impactful career in the semiconductor design and development. His technical interests include VLSI architectures, ASIC, FPGA, and SoC design, and he has been actively involved in design and EDA support for various industrial client projects as well as academic training initiatives at Entuple Technologies. We are delighted to have him with us today to share his valuable experience and insights. Now, I take this opportunity to warmly welcome you, sir. The session is over to you, sir. Thank you so much.
thank you, ma'am. Thank you for the introduction. Uh, yeah, my screen is visible, ma'am.
Yes, sir.
Is my screen is visible, ma'am?
Visible, sir.
Thank you. Okay. So now, okay. So, thank you for the introduction and thank you for the opportunity to take part of this at an online FTP. So, anyhow, uh, as of today's topic, AI-driven ADA tools. Okay. So, before entering into this EDA tools topic, let me introduce a small basic introductions about our this semiconductor industry based on this VLSI, right? So, I think hope everyone knows this VLSI, very large scale integration. We are integrating millions and billions of transistors in a single chip, right? With the basic components of the MOSFET transistor. So basically, the MOSFET transistor consists of this three terminal, or including the four terminal device: gate, source, substrate, and drain. Right. So these transistors have the operations of switching logic between zeros and ones, right? And the main important point, and that's VLSI industry is our the technology. So the nanometer technology, right? So this nanometer technology refers the day by day the nanometer technologies keep on shrinking. So we started with 180 nanometer, right? Nanometer, it is in the three digit. Now we are using a single digit nanometer ICs. So, so how the revolution has changed the technologies, right? So we have started with the basic techno integration concepts. Then we have start reducing the number of the area sizes and the power. Now we are trying to adopt the automations also with artificial intelligence technologies, right? I think previous session also there. The VLSA have started with the CMOS technology, right? CMOS basic device. So mm, CMOS have more short channel effects will be there, and this is more comfortable for withstanding and reliability up to 28 nanometer. We start, as I said, this started with 180 nanometer, and it's working very well up to 28 nanometer. But if you go beyond 28 nanometer, the device withstandability is not able to withstand, right, for the lower technology nodes because of high speed of operation. And due to this high speed of operations, there is a huge amount of power dissipation will be happened, and this power dissipation will be appeared as a heat, and it is entirely damaging the ICs. So then we moved on to the next device called the FinFET. So with the multi-gate technology. So here for this high-end applications, right, as we go for this high-end applications, we need a high speed of operation devices. So we went for the another device called the FinFET, and this FinFET is used for the technologies below 28 nanometer, that is 80 nanometer and 14 nanometer, 10 nanometers also we are using with FinFET technologies. And still we have another one more alternate device is available with the CNFET, that is CFET, that is carbon nanotube FET. So here also we have less than 28 nanometer, we have both devices are available, FinFET as well as CNFET is available. And right now 7 nanometer also the products are coming, right. If you go beyond your 7 nanometer, even this FinFET and the CNFET also can't be able to withstand with the high reliability. So right now industries they are moving with a new device called the GAA FET. So this GAA FET will give you the multiple gate and multiple sources and multiple drains. Previously we have multiple gate structures and the source and drain terminals, but here gate, so surrounded by the gate, we have multiple sources and multiple drains will be there. By observing this diagram, you can able to understand this GFF device, right? So now industries are moving all ICSR fabrication with the help of this GAFF devices. And what are the important parameter in VLSI? As you know, the power, right? We are using the ICs in high speed computing. The best example of our ICs revolution is our processors, right? Particularly Intel processors. So Intel start with this i3 process, i5, i7, and i9. Now we are going with a high multiplications of tens of the number of transistors are doubling very fast in this series. So here you can able to understand this. So three i3 processor have the four cores with 8 MB of cache memory, with the operating speed of 3.8 GHz, and the power will be around 65 watts. So then again, we are focusing on this i5 processors with 6 cores, and we are increasing the speed with 4.1 GHz with the power same on 65, maximum of 125 watts. Then we are started for this i7 processors, right? So in this i7 processor, uh, we have 8 cores. The number of cores are increased to 8, and the same we increase memory core cache memory with 16 MB of cache memory. But here you can see that the frequency has been reduced from 4.1 to 3.8 as the lower frequency. But the speed, right, the performance will be high, and the power also remains same, 65 watts, maximum 125 we are using, right. Then i9 we are going with a 10 core processors and 20 cache memories, 20 MB of cache memory we are going with the same operating speed and power. So the speed of operation, that is the frequency, will be remain same except this i5, right. If you start increasing the frequency, not only the speed is increasing, the same time the power consumption is same almost, the but the power dissipation due to the high speed, a very high rapid speed of operation, we are getting huge amount of power losses as a heat. So in real time also you can feel that compared to your i3 and other process, i5 process will produce more number of heat dissipation. So that is the main disadvantage of this i5 processor. And Intel also they accepted officially, right. So In this, so in VLSI we are comparing, if you take any ICs, we are comparing with these three parameters: power, performance and area. So any parameters, any ICs will be characterized within these three parameters if you take anything, right? So the ultimate aim of reduction in area, also reduction in power, and increase the performance area. And also obviously these three parameters have a big trade-off between them, so we can't able to satisfy all these three parameters for any applications, right? We need to sacrifice, or we need to compensate with any one parameter which should be having the disadvantage. So disadvantage means it is a, we need to compensate, that we need to accept for the high speed of operation, right? Then integrated circuits with overall all our aspects we are using with RF applications, and RF also will be there. RF domains, RF parts will be there. Then SPI protocols will be there, memories will be there, and analog and mixed signals will be there, and the DSP process. So all things will be there for the IC. So inside this we have these ICs we are using with, wherever you, if you take any part of this electronic gadgets, we can able to see the ICs. So like smartphones, computers, any tablets or modems, routers, and now AI, right? AI required a huge number of the processors, right? So it completely, it is controlled by the ICs only. So the industries mainly they are taking on this, right? Nvidia processors, and Intel, Broadcom and Qualcomm and Apple, right? So these are the industries they are using. And the global foundries we have supported for all. So the world leaders in this IC manufacturing will be the TSMC. I think hope everyone knows that, right? Taiwan Semiconductor Manufacturing. Then we have global foundries. Then our tower jail will be there. Then we have a HP Hynix power domains will be there like this. And we have Intel as well as Samsung also will be there. Philips will be there. So Infineon will be there. So we have so much of companies are have for manufacturing the ICs foundries. So these foundries are producing these ICs in a huge numbers for the day-to-day life, right? And as Entuple, we are doing with the Cadence partners, and here we have the chip design with the Cadence according to the Cadence design flow, right? So we are selecting the foundry where you need to manufacture your IC. So based on that, you have to choose your technology. First, we have to choose the foundry where you are going to fabricate your IC, and which technology node you are going to use it. And according to the technology node, you need to use the PDKs, right? That is our process design kit for the libraries, complete libraries. Then install these PDKs in your any EDA tools will support, right? As we are supporting Cadence, so I just mentioned as Cadence, right? So we are installing and PDKs in Cadence and start designing in Cadence tools for entire RTL to GDS file. So once the complete design got ready, the GDS file got ready, so we are sending back to the foundries to manufacture the IC. So once the IC is manufactured, so again we are, after the testing we receive the IC and we are keep on progressing. I think it is clear. Okay. Right. So we have various EDA tools are there. So in ASIC design, particularly for the cadence, we have various tools are available for the design for ASIC in both full custom model as well as in the semi custom model, right? So full custom, we are starting with this schematic editor, and the design rule checks are there, and the simulator will be there. There is a spectre simulator, wonderful simulator for analog circuits, and layout editors will be there. Layout, Virtuoso layout. Virtuoso is the topmost tool in our cadence. Then we have our layout LVS process and the RC extraction we are doing for these analog circuits. And meanwhile, the other two big giants in this synthesis tool, Genus, and the physical design tool, Innovus. So these are the basic, that is the general tools all are using, right? And typically for other applications like analog mixed signal applications or RF mixed signal applications also, we are supporting, that is Cadence is supporting, right? So as I mentioned, we have two different methods are there, right? Semi custom ASIC and the full custom ASIC. So here you can see there's the semi-custom flow. Just for the understanding, we are just adding. So semi-custom flow starts with the specification, and based on the specification, we are developing the RTL code, and we are once the RTL code is developed, we are start working with the verification side, functional simulation or functional verification. Then after functional verification, coverage analysis, and we are going for the synthesis side. Then we have the timing simulations will be there, that is our GLS. Then we have the backend side, floor plan, power plan, then placement and routing, CTS, that is clock tree synthesis and routing, and GDS. The complete flow will be carried out by incisive simulator or the Exilium simulator and the genus synthesis solution, and finally Innova's implementation system for the backend design. So still we have lot more tools are there for the individual process, right? So that's the one for semi custom flow. And comes to the full custom, that is custom IC flow. We are starting with the schematic. We are doing both the side RTL to GDS as well as schematic to GDS. So in this schematic entry, and once the schematic entry done, then we are going for the simulation and the layout process. After the simulation is done, we are going for the layout. In this layout, after the layout is completed, then we are going for the physical verification side for DRC and LVS. So for that, we are using this Asura tools, and after your physical verification, we are doing the RC extraction, and after RC extraction, we are going for the back annotation process to verify your post layout simulation. So once your post layout simulation satisfies your requirement, then we can go for your GDS IA file generation process. So these are the two main flow methods we are working in industries, right? Then here, as we mentioned, so these EDA tools will provide the automation of IC, how the ICs are manufacturing, right? And here, these are some steps we are doing, right in the schematic side, other that is in the full custom side we are doing, and layout verification and synthesis, placement of the complete process we are doing. So these are the EDA tools we are doing as of now. So what is the impact of AI in these EDA tools? What makes them AI driven? So that is what the main thing. So the AI driven EDA tools that, as you know, AI have the various algorithms are there in AI as a small thing, right? Machine learning algorithms will be there for predictions and generating various pattern recognitions, and the reinforcement learning will be there, and natural language processing, NLP, before the design intent interpretations. Then we have a big data analytics for the bug prediction and the performance estimation. So this data analytics will help us have the huge data we are analyzing, and based on this data analysis, it will produce the output. But everything will be happened in a fraction of second. That is the very important thing in this ADA, AI driven ADAs. So the main key applications of AI and ADA. So as I mentioned, the design space exploration, right? That is quickly how fast we are evaluating the solution for the given problem, right? And the given steps, how many steps are there? Because as you know, while we are integrating this IC, right, transistors and counts of millions of transistors, that time is very very important thing. So the execution time right now, we are working on a number of days to number of weeks. We are working on the one step to another step. So this AI will make you this time will get reduced, that the reduction time reduction and the timing closures. So predicting and fixing violations automatically. We are this violation fixing is an very big task while we are doing with the huge, that is um, uh, high density applications, right? Then power optimization, if you comes to that. So your machine learning models suggest your power efficient configurations and various algorithms it is doing for the power optimization as fast as possible. How much do it is doing. Then your bug detection, while performing this verification side and all these things, this bug detection is a very very important thing. So how much bug you are detecting and how these bugs are fixing. So this is a very big task in our complete chip design, right? So once all these things are got ready, right, your timing, your space, that is your area, as I mentioned, the same three parameters: area, performance, and your power. So based on this, your all data will get going. Okay. So as for this, so our ultimate aim is this so the final IC manufacturing, right? So in the IC manufacturing, we need to produce a good number of ICs compared to your faulty ICs, right? So this EDA will produce a high yield productions. So that is the ultimate goal of this AI in the EDA tools. So these are some examples. Also, various EDA vendors I have listed here. So here in this listed EDA partners, right? EDA tools. What are the AI tools they have introduced recently? So Synapses, they have used DSO.ai as an AI reinforcement learning for placement and routing (PNR) and synthesis for their doing automations AI features in the place and route and the synthesis process. And our side, our cadence, we are using the Cerebrus tool and the machine learning for complete RTL to GDS flow optimization. So we are trying to optimize the complete flow with the ML algorithm with the various different stages, right? From RTL to GDS, we have many stages are there. So all these stages are we are trying to do the optimization through Cerebrus. Then we have mentor Siemens, that is our mentor graphics will be there. So there they are using this Solido ML platform. So particularly for variation and the simulation side, as I already know that Siemens are very much stronger in testing of these ICs. Tessent, they have a good tool. So along with that, they are introducing this AI for doing the optimization process, right? Then Xilinx, they have added Vivado, right? Previously, it was there with the Xilinx ISC shoots will be there. Now, this entire ISC shoot can be removed, and the future will be your Vivado tool only, which is using the ML based tool only. So for doing this faster compile times and better quality of results and the prototyping. Mainly, as you know, the site we're using this FPGA is the Xilinx is the leader. So there they are using their quality, the prototyping method, how fast and how much density can able to use it in the ASIC ICs. So these other companies, they are introduced various EDA tools in a industry. So benefits in area, as I mentioned, so we are getting more faster design cycles, 3x design cycles, and the improved quality of results will be there in terms of PPA, that is your power, performance, and area. Then automated design making in complex workflows will be there, and scalability with large design databases are there with the cadence. The main thing, revolutionizing semiconductor design with AI, right? So AI is impact on every day to day life, right? We are having right now, we are using these AI products, right? So all these products are having the high impact in the semiconductor design in next decade particularly. Okay, so in this, the main thing, as we mentioned, so the PPA, that is optimizing PPA, right? Optimizing and automating this chip design through AI. How it is happening? So the main thing is we need to parameters of the IC's PPA parameters optimizing. So this AI analyzes your human designs to optimize power consumption, consumption, as well as then performance and the speed utilization, space utilization, right? And AI explores multiple design options quickly for identifying the best components. And while doing the automating of chip design task, that is the main task is our backend portion. Compared to your front end portion, logic backend portion have the very high accurate process. So this AI tools will automate this process, place and route, and debugging this. It make it automate to reduce the time, and it generates optimal layouts, right? So as we are doing manually some process in the layout, that is having, it's not that much accurate one. So this AI will give the reducing time, right? The minimum area will compact the designs, it will do the layouts. And AI algorithms can explore multiple scenarios, suggest best options for doing this modern chip design process. And the bridging the chip design talent gap. If you see this, these AI tools help overcome the shortage experienced engineers. Right now, we need in India, we need more number of semiconductor engineers are required for the next decade. So for that, AI is one of the best replacement, and we need more things, right? So this supports the growing demand for semiconductor chips driven by electrification. That is our automation. So as I mentioned, AI helps optimize the PPA, that is power, performance, and area of the ICs. Efficiency, right? AI quickly identifies the area where we need to do the optimization reduction process and reducing the power and the performance level, that the speed, right? It do the how we are doing the optimizations. Compared to that, AI will do more optimizations. And space optimization, compared to this area side, AI suggests design same performance with the high space ICs, because your IC will give you the high difficulties, right? The difficulties will be more. The new problems will arise every micrometers of area reductions. So this we will identify, and this AI will shut out these type of issues. And as mentioned, AI chip design task, as I mentioned again, this place and route is the very critical task for in the chip design flow, right? AI allows this exploration of multiple design scenarios and for complex ICs. So this bridging this talent gap in this chip design will be done with the help of these AI tools. And these AI tools, how it is get the repeated iteration, how it is get doing. So that is what this very important thing. So in cadence, so we have various AI generative applications are there, that is tools are there. You can see the out of that the most one thing is the Cerebrus for the complete digital design. As I mentioned, various domains are there. In each domain we have the influence of this AI. So this cadence, that is our joint enterprise data and a platform, that is your ZA platform, will give you. In the digital side, digital IC design side, we have a tool called the Cerebrus. And in the analog side, right, analog or custom IC design side, we have the high newly efficiented Virtuoso Studio will be there, which is a high-end application. Right now, we have introduced recently it is introduced, and Verisium debug and verification. So for doing the verification side, front-end verification, as I mentioned, so the entire IC design, the most of the time is spent on this verification side, and this will be automated with the help of this tool called the Verisium, right? And comes to the PCB side. Once these designs are completed, we need a PCB. So in that PCB side, your Allegro will take care of this, right? Allegro, your PCB board design, Allegro will take care of. Then we have this multiphysics optimizations will be there, which is called your tool called the optimality. Okay. And this cadence cerebrus intelligent, right, as I mentioned. So this is our cadence our tool, that is cerebrus, having the high control over the entire RTL to GDS flow, right? So you can see here chip explorer revolutionaries, right? So here we have this better PPA results as compared to your previous sites. Okay. GDS flow, and the cadence cerebrus has lot of possibilities and combinations of different tool settings, so for scalability and your improved productivity. And we have the better RTL to GDS optimizations, right? So here you can see this this is where overall cerebrus overview, where we are giving this design RTLs to the design RTLs and design goals with the constraints we are applying to this cadence cerebrus. And here you can see various scenarios will be there. Scenario starts with the scenario 1 to scenario n. We are using this distributed architecture, so the number of steps we are doing, right? So cerebrus genus and cerebrus innovus and cerebrus tempus. So what are the basic tools we have? All these tools are automated with the cerebrus. So with the each and every tool, genus for synthesis and innovus for PNR and tempus for timing performance. So all these metrics are put together with the multiple scenarios, and finally this AI will optimize the AI driven engine will do the optimization process, and Cerebrus optimized ML model, you will get the output. Then what is the Cerebrus workflow, right? So earlier we are doing this RTL design, right? So Cerebrus optimized flow will be there after this ML model. You can see this RTL and the final RTL design, that is our final before going for the physical design, right? So what is that RTL? Then current Cerebrus optimization flow will be there. Then for the tape out, for particularly mainly for the tape out, we need more automations are required. So there we use this genus Innos and Tempest tools for the tape out database. So the flow will retrieve for design to design. So in this, what are the main components in Cerebrus? You can see that the first thing is your primitives. So different options and different recipes will be there, which are all built in and user defined parameters for floor plan and library costs and design constructions. Okay, and we have a various scenarios will be there. All these scenarios will be automatically. It is created by Cerebrus, right? Then the main objective and the final one is your the cost effective. The cost effectiveness is the very very important parameter in designing, right? So we need to reduce this cost one. So this will take care of this Cerebrus. So here, what is the runtime improvement has happened in this Cerebrus RTA, right? Cerebrus runtime improvement strategies. So here we are using with this genus synthesis flow, right? Joules replacement will be there. RTL generic synthesis mapping. Then we are optimizing with DFT, right? So this DFT netlist will be a main thing. So this netlist will be handed over to the physical design, that is your PNR. So this genus Cerebrus, right? Previously it was this process. This is the old one, earlier one. Now after this Cerebrus have added, so RTL synthesis generic and synthesis mapping, right? You can see here reduced number of intermediate databases and files will be there in between your mapping database and the spatial database. So this will produce 30 to 40 percentage of the runtime improvement scenario, runtime improvement in the entire RTL to GDS flow, right? And you can see this Cerebrus runs with multiple runs, that is parallel concurrency runs will be there, and running with only dominant timing and power corners mainly to reduce your save runtime and the memory. Then skipping the modest DFT stage. Right now we are developing the ICs including the DFT stage. So in this new model one, right? So here we are removing this DFT and we are instead of this DFT. So DFT is again the big process to test your net list, right? So then only the necessary files and the databases only it will save it in the our database. And this runtime Cerebrus is still converged with even after many methodologies have introduced, and multiple blocks are running parallelly by the single user, right? So here A enabled Cerebrus chip optimization flow as we've already seen. So initial and the design RTL will be there, tool options, and what are the tools we need to use it that you can give it, and design constraints and the library options. So what is the library? You are going to use it for the ML. So right. So in this we have a high productivity optimized PPA, so reduced testing, and high predictable and high yield of application, right? Prediction yield one. So here ML algorithms for IC design. So we have supervised learning, unsupervised learning, and reinforced learning cases will be there. So you can see this supervised learning with physical analyzers. We have a various layout patterns will be there, right? So where we have this Pegasus, one of this latest tool will be where Pegasus for the layout pattern analyzer. So and it will quickly detects and automatically fixes this lithography side, manufacturing side. Sorry. Okay, right. And this cadence litho physical analyzer. So this is your manufacturing side. So while doing this lithography process, we are using these methods. They are using, right. Then this cadence verisium. This is a previous one is a cadence Pegasus. We are working with supervised learning learning mode, and cadence verisium, as I mentioned. Right, so these things will be there. So reinforced method we are using with the cadence cerebrus. So Pegasus and verisium and cerebrus, so these three are very important things in the uh, AI process. Okay, so these are some introduction about this EDA tools. Let me take this to our actual flow, where we have this cadence will be there. Okay, so these algorithms we are using in various applications, right? These tools. Let me take a small introduction about in this cerebrus, as I mentioned, right? So this process, right, genus and cerebrus process, right? We'll see this in the synthesis side. So just a minute, ma'am. I'll just take one more slide. just sorry for the product interruption. So just with another flow, I think screen is visible, right?
Yes, sir.
Yeah.
Its name said, yeah, now it's visible, sir.
Yeah, yeah, it's got it right.
Yes, sir.
So as I mentioned, right, in our process, so entire thing, right, and the small thing will in detail we'll see this flow where we have mentioned whatever I have mentioned, this genus and synthesis, right? So in this synthesis flow, right, starts with the RTL code and the functional simulation, right? Then we are going for this once the simulation is done, right? RTL, we are doing with the RTL verification. So once RTL verification is done, that is we are doing the functional simulation for the small task, that is small blocks. And if you go for the high-end applications, right, so we are going for the complete chip level verifications we are doing with various test cases, right? So this complete test case scenario will be automated through this cerebrus, one thing. Then we comes to the logic synthesis stage, right? So in this logic synthesis stage, we are adding the technology libraries, and here, as we mentioned, the timing, area, and power analysis, this PPA parameters we are analyzing here with the zero net delay. That is the main thing. Then we are going for the back-end process with the complete physical design automated process. So this process will get automated with the help of this cerebrus. So for doing all this physical design, we are using the tool Innovus we are using. Okay. So for doing this back-end process, right, after the physical design, so this STA process and the physical verification process are very difficult, and here the full automation comes into picture here. Okay. So the this process, right, DRCs. So as I mentioned, this physical verification, right, so DRC and LVS process will be done with the help of our Pegasus tool. So this Pegasus, again, we are running with the supervised learning, right? The supervised learning will be taken care with the help of this Pegasus and DFT, right? So the complete DFT. So here the entire DFT process is skipped, and as you mentioned, once the cerebrus model, that is where AI has been introduced. So we are trying to avoid this DFT process uh, in the entire flow, right? So instead of doing this DFT side, right, we are avoiding, and instead we are giving more time, and we are running more number of iterations of simulation, so more number of iterations in the synthesis and the physical design side. So as we mentioned, so here you can see that the entire process earlier we have added with the DFT process, right? So logic coverage analysis will be there, and DFT designed for test synthesis will be this in the synthesis side. So generally we are doing the logic synthesis phase, and once the logic synthesis is completed, we are developing the gate level netlist, right? So this gate level netlist we are adding with the technology node and the DFTs, right? So the mainly these DFT insertions will be happened after the logic synthesis. So once this DFT is completed, right, design for test synthesis is completed, we are running for the ATPG vector generation, and this ATPG vector generation uh, will develop and will generate the test sequence, test vectors to find the various faults. So after this, we are doing this logic equivalency checking process, where your complete logic has been verified or not. So this complete logic, that is your whatever the logic inferred in the RTL code, which has been completely developed in the synthesis stage or not, which is going to check it, which is called your logic equivalency checking. So this logic equivalency checking, we can do it at any stage after your synthesis process. So once your synthesis process is get ready, right, then your synthesis report, right, after your floor plan, then we are going for the physical design side. So once in this physical design, floor planning, power planning, and placement, CTS and routing has been completed. So after your routing is completed, again we can go for the logic equivalency checking between your routed design and the synthesized design. So in between, you can able to check the logic equivalency. In the meanwhile, you can check the logic equivalency between your RTL and the routing stage also. So these are some other stages we can do with the LEC checking. So after all this checking, we are going for the final, that is your STA timing closer. So where we are doing the timing analysis portions here, that is our static timing analysis as well as dynamic timing analysis also there. But comparatively, static timing analysis will be most frequently we are doing, right. Then we are doing with a gate level simulation, right. So the layout, once the layout and the sign off has been completed, then we are doing the back annotation. As I mentioned, the back annotation process with get with post layout, which is nothing but post layout your simulation process. So once it is got satisfied, then we can uh, generate your GDS file for the fabrication process. Okay, so these are the design steps we have there taken, and at the end you can see that synthesis side, right. So for doing this synthesis side, so here we are using the technology adopted by using this the Cerebrus and Cerebrus integrated genus, right. So this is with respect to the technology foundry, right. Whatever the foundry uh, you are choosing, right. So based on that, you need to download, you need to get your PDKs, as I mentioned in the flow, right. This process design kit libraries, you need to add it. Then you need to add your RTL code, that is your Verilog code, you have to add it. So after adding your Verilog code, you need to add the constraint file, right. So this constraint file is nothing but your complete information about the clock signals and libraries, right. Come to the library side, the main important thing is what are the timing libraries they are adding, what are the technology libraries they are adding, and what are the macro files they are adding. So all these things are very, very important. So based on these libraries and RTL code, so these two things are very much important. And furthermore, we need a more input and more details are required with respect to the constraint file, because this constraint file consists of your complete information about your operating frequency control. So your entire chip operating frequency will be controlled by your constraint file, and this constraint file will determine the number of gates of the design, right? So if you are for the simple analysis purpose, if you keep on changing the constraint, right? So the number of gates are keep on changing. That means your number of gates, right? So if the number of gates are changing, automatically your area also will get changed, right? Then automatically your power parameter will get changed and your timing parameter also will get changed. So all this to put together and will create a synthesis process with a various efforts will be there with either we can do with a low effort, what will happen, and if you do with a medium effort, what will happen. We will we can able to analyze, and you can able to compare in each and every step what is happening, and how much net list it is producing. So these things you can able to analyze by using the synthesis, right? So that is about the synthesis. Once the synthesis is completed, then we can generate, you can get your complete net list for the design. So this net list consists of your different components, that is your basic combinational cells, that is simple combinational cells, then your complex combinational cells, then you have your sequential cells will be there, then you have your basic cells will be there. Then other than this, you have some miscellaneous cells also there. So including all these cells, you will get the complete gate level netlist you will receive. So other than this, you will get the reports of area, power, and timing. Thus, again, the PPA parameter will be very, very important here. So, the parameter analysis, whatever the analysis we are getting here, is an approximated analysis, power, performance, and area, right? So, once the physical design is completed, then you will get the complete uh, your PPA report, right? So other than this, you will get a one more important file, as I mentioned. With respect to this constraint, input constraint file, the tool will produce the output constraint file. So this output constraint file is very important for the complete process. So if any one process is getting wrong, means the entire process will be repeat again. Okay, so that much important your output process. So in the output file, there are some measures will be there, metrics will be there. So by using that metrics, we need to limit the process, right? Limit your output constraint files. Then next one thing is your conformal LEC, right? As I mentioned, so this conformal equivalency checker, that is your logic equivalency checker, we can compare with this RTL with any stage of your design flow. You can see here RTL and logic synthesis, you can able to compare it. Then logic and RTL, your RTL code and your logic optimization steps, right? After your optimized optimization, what the netlist you got, that you can able to compare it. Then your DFT process, test insertion will be there, and clock synthesis, right? So after your test insertion, that is your DFT process has done, then you can after this DFT process, you can able to check with your RTL code also. Then you'll see the synthesis flow, then your floor planning. So floor planning, you will just have the area size, right? So how much silicon area you are going to use it, so that you can able to compare it. So after your floor plan placement, that is your power plan and the placement and routing. So once this design, that is your physical design, is completed, that's why it is in three stage. So all these stage, the routing input also will be applied to the LEC checker, that is your logic equivalency checker, and will check the output. So after optimization, you can do it. Then after ECO, that is your engineering change order, right? So after your engineering change order, so what is the optimized netlist you got? So this complete netlist will be given to the LEC module, and you can do it. And this LUC, what is the operation is behind that. So the main operation will be done in two ways. Two modes of operations will be there. One is in the setup mode, another one is in the LEC mode. So setup mode, we can add your golden design and your standard, your PDK libraries, then your devised design library. Golden design. So it's muted. So golden design and the standard libraries and the revised designs. So these all things are put together in the setup mode along with the constraint file, as I mentioned, right? So constraint is the very important file while doing the synthesis process. So after adding this constraint and the libraries, then we are comparing your golden design and the revised design. So golden design is nothing but your RTL code only. So then initial stage, the revised design is based on the synthesis, either logic synthesis or the physical synthesized netlist or the logic optimized netlist. You can able to give it as a input as a revised design. So then you can switch over your setup mode into LEC mode. So in this LEC mode, we will specify compare parameters. So what are all the parameters you need to compare with your golden design and the revised design, right? So once your comparison is done, right, your compare design. So if your comparison points, right, parameters will get it will not get matched, right? If it is mismatched, then we need to diagnose the mismatching points, right? So you need to diagnose the mismatching points, and again you go back to the specifying parameters, and you need to based on the diagnose, and you need to, if possible, we need to change the golden design code also. Why it is get miscompared, so that you need to analyze. So once this diagnosis is done, right, your parameter, what are the parameters you are comparing, right? So once all these things are completed, then you can do the comparison again. So this comparison, right, so this comparison will give you the detailed report. So once this miscomparisons has been removed, right, then you can go for the equivalency checking. That is, equivalence checking will be completed. So once your comparison will be 10 to 0, right? So your miscomparison will be 0, means there is no miscomparison. So all the points are matching, so that we can able to convey that your entire process is uh, completed with zero, right? So zero misleading points, so that we can able to conclude that the miscompared points are optimized by using this LEC method. That is your logic equivalency check method. So stage by stage, here also, here we are doing multiple iterations and multiple checkings we are doing for the optimization process. Okay. Then next one is your physical design, as I mentioned. So physical design, what we are doing, the logical netlist will be converted into physical netlist, or we are the mm, we are placing the entire netlist into the core area, that is your silicon area. How it is get going to place it, and how it is get occupy your silicon area. So that is what the complete physical design process will initiate. Okay. So like your synthesis process, your physical design process also requires multiple files. So in detail, if you see this, so the most important file is your gate level netlist file, what you got it from the synthesis side. Then you need a logic library. Then you have the constraint file. So again, this constraint file also we got it from the genus tool, not for the input constraint side, right? So what are the constraint parameters you have mentioned, so that is in different, and the output input consent is completely different, right? So we, after adding the gate level netlist and the timing library and the constraint file, you need to add your physical libraries. That is why the physical libraries will give you important process. So after your physical libraries have been added, so then we are doing the def process, which is called as that is your lib we can call it as a left folder, that is library exchange format file, or here the text exchange format file, def file will be there. So by reading this def file, that is your tf file, right? So your core region will be matched with the actual silicon region, right? So with the help of your process called floor plan, power plan, placement, and uh, routing, right? So once all the steps are completed, then we are entering into the main site called your timing sign off site. So here the timing sign off will plays a very important role for the timing optimization. So once all these things, so for doing this timing optimization, we need to add all library files. So that is our min max typical files will be there. So all these min max typical files need to be added, right? So finally you will get the optimized netlist, you will get it, right? So then along with the optimized netlist, you will get the PPA reports. With the efficient PPA reports, you will get it. That is your power performance and area reports. So physical design flow, as we mentioned, so this physical design flow consists of various stages other than your process, whatever we have discussed, right? So gate level netlist we are adding, and we are adding the libraries, then we are adding the floor planning, then power planning, placement, and clock tree synthesis we are doing, and we are doing with the routing process, right? And here we are doing with the RC extraction step. So after the routing process, once all the network layers are completed, so we need to extract your RC value. That is your main goal to reduce the delay, right? So as for this RC combination will be your register and resistance and capacitance extraction from the circuit, right? Once these values are extracted, so based on this product value of your resistance and capacitance, your delay will get reduced, so that you can able to optimize, that is you can able to get the optimized circuit, you can able to get optimize the physical design, you can able to achieve it. So once it is done, so the physical parameter will be there. So the physical parameter, right? The physical parameter, that is your physical verification, which is done with the help of your Pegasus, as I mentioned. So this physical verification includes your DRC LBS. As DRC we have so many number of DRCs are also available. Okay, so all these together put together, you can compile and you can analyze it. So finally you will get the GDSIA netlist, you will receive it, right? So this GDSIA file generation will be happening, and this you can able to read uh, at at your chip level, right? So this GDS file has been given to the chip manufacturing, right? Manufacturing unit. So the manufacturing foundries will, like as I mentioned, TSMC, Global Foundries, Intel, Corel, or you have right. So by using these various vendors, they will read this GDS IA netlist file, and will give it to you the complete IC. So what is the expected IC you got it, right? So this is the flow you can have. So there we can able to see in detail about each and every steps will be there. Floor plan and power plan and what is these things. So floor plan means the how the complete IC will get designed, right? So here the complete tool process, as I mentioned here, the tool for this complete Innovus, that is Innovus is the tool for producing the complete physical design. So this will be automated again. So here in the floor plan, so we need to plan your size of the IC according to the customer specification, or based on it, either you can do it square based floor plan, you can do it, or rectangle floor plan you can able to do it. This rectangle means that depends on the area and width of the design, right? So area and width of the design you can able to change, they keep on changing your floor plan size, right? So once all these steps are over, then we can go for your to complete the next step, that is your padding method, right? So here you can see the IO pads are added with various tracks. So each and every IO pins, right, in the netlist, gate level netlist you are generated. So this generated gate level netlist will get mapped with the IO pads of the technology library. So in that IO pad, how many number of IO pads and corner cells are required, and any macros are required, and all these things you need to understand it. So based on your number of macros and your IPs, right, we need to choose the remaining space or remaining area for the logic cell placement. Okay, so that is what done in the first stage called the floor plan. So in the second stage you can see that power plan. So in that power plan you can able to see this, the I IO pads are matched. The previous one is the that is a square based floor plan, and this one shows the rectangle based floor plan. Okay, and here, right, so in the power plant the main two things we need to see is, one is your congestion analysis and another one is your power analysis. So here power dissipation will be very very high in this stage. Your motherboard have high speed of operation. After the high speed of operation, right, it will try to manage with the operating speed, sorry, right? So and this power plan will be done in three different ways. And through the power pad carries your VDD and VSS around your core area. You can see that. So the entire core area will be surrounded by the power supply, VDD and VSS. So in between your core area, you need to draw some stripes. You need to allot some stripe lines, that is vertical strip lines for the macros connecting or IPs connecting. So this also you have to add it, right? Right, your rails. The third one is your rails. You can your entire netlist, that is your core area, will be divided into multiple rails will be there, that is channels. So each channel, the rails will get flow over top and bottom of the channel. So the entire channel will get occupied by VDD and VSS. Okay. So then you have the placement activity. So you have the placement activity. So how much total wire length you are going to use it. So you need to reduce your wire length so that you get memory size, right? Minimize your chip size and your cost also, expansion cost also you can able to reduce it, right? So then your timing and the clock cycles, clock cycle of your chip is limited by the delay of the longest path, right? So which is the longest path in your design, so that you need to analyze it and you need to get back, right? So then the main thing is your avoid right? So the once the congestion analysis is happened, then we are going for the reduction of power. So how much power you can able to reduce, so that we are focusing on this reduction in the power. So this evaluate hotspot, that is hotspots will get created in the defined area. So these hotspots will be identified and overcome by that another tool of voltage tool, right? So in that you can see the temperature gradient also, you can able to see and you can analyze it. And a secondary objective of placement you can see here. So the secondary objective of placement tool is running time minimization. So how much time you can able to minimize it, so that you can able to do it. That is what the secondary objective, right? Minimizing your runtime, that is very very important thing. So all these things are put together in the placement side. So then you have this clock tree synthesis, as I mentioned. So clock tree, from the clock shows how the flip-flops are receiving the clock signals. We call it as your the difference will be your clock skew, right? So this main goal is you need to check your clock skew. Minimization is very important. As we mentioned, you can see a small understanding, right? From the clock source, these yellow color registers are placed at different intervals. So initial stage of flip flops will receive some clock signals at some nanosecond time. Then you need to check whether if you consider the first row of your flip flop and the last row of flip flop, how much time it taking to reach this flip flop to activate it, right? So this you need to identify the difference, and this difference should be optimized, right? As we mentioned, so this should be optimized by inserting various buffers in between the logics. So this you need to add it. Okay, so once this is done, right, your buffers will be added. After adding the buffers, you will get the uniform distribution of your clock. So after that, we can go for the routing process, and the entire routing we can see based on the technology node, right? Either 90 or 45, or even if you go for the lower technology nodes, right? Your routing will be very very important, right? Your routing will be very very important. Your routing consists of various layers. That is what I'm trying to explain. So these number of layers will be starts from metal 1 to metal 9, or even some technologies it will go up to metal 15 nanometer, and 5 nanometer designs will have up to layers, up to metal 15 layers are there. So that much fine accuracy will be there, that much fine tune of routing will be happen. Okay, so for including all these things while doing this routing process, all the layers you need to do the routing properly. So that is the main concept of this routing. So then we have a STA process. So you can see here timing reports are generated by STA tools, as I mentioned in the Tempest. So the Tempest is the tool, it is purely dedicated for the timing analysis. So where you can able to find timing violations such as setup violation and hold violations, to determine the cause of your violation, or appropriate to fix the violations, right? So for this input and outputs of STA, we can see here libraries same, right? So all type of libraries you have to add it, both liberty as well as your physical library. Then you need to add your gate level netlist, GLN or GLS. So here it is GLS because we need to add with the timing reports, right? Then synthesis will be happen. Then your timing reports will give you how much time you have taken for the complete design process. So this you can achieve it, right? Then you can go for the power analysis. So here for the power analysis, you need to go for your voltage tool, and here you can analyze not only the power, including you can see this, including the leakage, internal and switching power. All these things you need to focus. And EM, that is electromagnetic effects, and ion drop, right? Any voltage drop will be there inside your logic. So these things also verified in the packaging process after the manufacturing, right? Now all the symbols, right, all the analysis of this timing analysis, power analysis, and the area analysis has been done. And this particularly, this power analysis will be happened due to the voltage too. Okay. So IR drop is the main parameter. So the power supply, that is, and your ground supply voltage across the design chip. So your across your design, the metal layers have finite amount of resistance, right? Finite amount of resistance and capacitance will be there. The most thing, right? So here the metal layers have finite amount of resistance, and this resistance will be limited with respect to the area report, that is the area power and analysis, right? Whatever we have analyzed here, it is a voltage drop, or we can see this IR drop will be there, right? So this IR drop will give you some cases you can get bonds, or most of the cases your voltage drop will be very fraction of second will be there. So immediately the last signal will get recovered very fast. So finally, we'll do with the physical verification, DRC and LVS. So DRC will check what are the active to active spacing and well to well spacing and minimum channel length of the transistor, and the minimum metal and metal to metal spacing and electrostatic deflection. So all these things will be under your DRC. And LVS, right? LES will give you the analysis, that is your layout versus schematic. So the layout, whatever you have drawn, it is the topmost layer layout, and the layout it is generated will be your complete IP based designs, right? So, right, so the optimized design, the errors will get removed, and so the optimized design is getting ready, right, to opt the lowest level, right? So then again you can if you want, you can able to do with the equivalency checking at different level, as I mentioned, right? For the backend side also you can able to do it. So at last finally you will generate the uh, GDS file, right? So this GDS file is a completely now it is currently owned by our Cadence Design Systems. So the entire pattern will be under our Cadence control only. Okay, so these are the steps we are doing, and so Abhigenta is our training side. We are placing the gap between your industry and the academic. We are fulfilling with various training activities now. Okay, so that's what. And thank you. And this is about what are the tools are available in the AI side, and so what's the design flow and what are the steps we are doing. Okay, so over to you, ma'am.
Um, Hello, sir. I'm Dr. Ashutosh from SRM IST Ghaziabad
Yes,
campus.
sir.
So I have one question.
Yes, sir.
See, mostly for the design
Yes,
of
sir.
these things, we have EDA tools available. and most of the EDA tools are basically
Yes, sir.
proprietary tools actually, like Cadence or Synopsys. These tools are there, which is costly,
Synopsis
and
work.
all the tools are mostly not available in all the colleges. So can any tools are there? Like Verilog, we have
Okay.
some tools. Like any other tools are there for like physical design
Okay.
or for floor planning, which is open source tools which are available to us that we can use both for the general purpose or for research work or something like that.
Some tools are available, sir. Actually, open source tools are available, but so this open source tools are what do you say, it is exactly not matching for the industry standard for the manufacturing side. So I'm talking about the manufacturing side. So these tools are the only authorized for the global foundries. All global foundries, they have accepted these tools. So but I'm not sure about it. We have a lot of tools are available open source, but the tools are up to manufacturer level, it will support or not, I'm not sure about it.
Okay.
Yeah,
But for a general purpose, for the in order to teach the
for
students,
analysis
we can
and
do that, right?
this purpose you can do it.
Okay.
Yes,
And
sir.
can you name something that like that in the chat box somewhere so that we can
We'll
able
see, sir.
to
I'll
get
just because as we are mainly working on our currents only. Some
Yeah, I know
tools
that
are
Entuple is
not.
basically are the license partner for the Cadence. They provide
Yes,
basically
yes,
Cadence
yes,
actually.
sir. Yes, sir. Yes,
So
sir.
we
That's
know
why
that part.
we are doing that. We'll encourage and we'll share it, sir. We'll see.
Yeah, thank you, sir.
Thank you.
There is a question in the chat box, sir. Can you
Okay.
briefly explain on .lib and .lef files?
Okay, myself, Kistara, sir. Okay. So this lib file is mainly for the information about the standard cells, mainly the timing informations. Other than logical, that is the functionality, the main information about the timing, the complete timing information about your basic cells are available in the lib file, lib library, and the left file is your layout exchange format file, completely information about the physical design, that is the physical parameters of standard cells, like your metal layers, how many metal layers are there, how many metal layers are used, if you use different metal layers with the different rectangles, right? So different sizes, so what is the resistance and capacitance will be formed. So these details will be available in the left files. Okay, so that is what the main difference between your dot lib file, we call it as a liberty library, and left file is your library exchange, that is layout exchange format file. So difference between lib file and constraint file. Lib file, as I mentioned, library file is different and constraint file is different. Constraint file is completely the information about the clock signals and the delays. So the timing informations we are mentioning, particularly on the delays. So which tools comes under PDK cadence? Which tools comes under university bundle? Is advanced CMOS technology after ML optimization from how to cross verify functional verification of converted GDS format as it follows specifications. Present EDA tools are there. Are they support three-dimensional mouse devices? If support, it's free evaluation. So as of now, all these questions, the first one by one I'm adding. Uh, for PDK, we have both analog and digital will be there. So that is where full custom we are using a Virtuoso Studio we are using, and for semi custom we are using Innova's implementation systems. So both will accept PDKs. So that's the first answer. And the second one, which tools comes under university bundle? And so right now we are revised in the year 2025. We have revised as entire level 1 bundle, right? Level 1 and level 2, that is your entire RTL2 GDS files will be under level 1, and RCAD tools will be, that is PCB tools, under level 2. That is the one. Then after ML optimization from RTL to GDS, how to cross verify. So functional verification and converted GDS format. So there is a metric called the coverage analysis, right? So through coverage analysis only you can able to closer your verification process once you met 100 percentage coverage analysis. Once you got 100 percentage of coverage, then you can say that your process ML, right? So we'll decide it how much verification has been done, that you can do it. So right now, three-dimensional mass devices also, Kerens, we are supporting three-dimensional mass devices also. We have the tools we are developing. Any other questions? Or to do PhD work, I think Cadence tool is costly. How to overcome this for those who are not affordable? Free source has lot of limitations. So that's what I said. Free sources are available, but with limited supports will be there. But if you go for now, if you think about industry standard cadence tools, that means EDA tool and the academic standard EDA tool, it's cheaper only, because companies, corporates, they are working with a very huge amount will be there, but for academic support they are offering with a less cost only, as of my knowledge. Yeah. Any other questions? Over to you, ma'am.
Thank you so much, sir, for accepting our invitation and then sharing your expertise with us. Now I invite Ms. Senthil Priya to deliver the vote of thanks. Over to you, Priya.
Good evening, everyone. It's my privilege to deliver the vote of thanks for the session on AI-driven EDA tools. On behalf of R.M.D. Engineering College and Department of ECE, I sincerely thank Mr. P. Rajendran, Field Application Engineer, Entuple Technology Private Limited, Bangalore, for being with us today and sharing his valuable insight. Sir, your discussion on integrating AI with EDA workflows and bridging industry and academic perspective has been highly informative and inspiring. We are grateful to you, sir, for sharing your expertise and making this session truly enriching for us all. Thank you, sir. Thank you so much.
Thank you, ma'am.
Thank you, participants. Let us meet tomorrow in day 4 session. Thank you all.